right, so the Phong shading model that we just looked at here is a very simple shader, which just allows us to start understanding the basic components of BRDFs. Now, when written in this form, we can see that the model itself contains the cosine factors of the normal vector and incoming light vector, as well as the cosine factor of the view vector and the ideal reflection vector. In practice, though, and in the context of how BRDFs are used to calculate the color, essentially, or the light reflected off a certain surface point, we like to generalize things a little bit more than this and actually take these cosine factors out of the material model, have them as separate terms in an equation, and really just generalize the actual shading model itself, or the specifics about that shading model, whether it's a Phong model or any other model, like maybe a Blinn or a Lambert model or what have you. We like to generalize things a bit more, really just as a function of the incoming light vector. I'm just going to call that L, and the view vector, let's call that. Actually, you know what? I'm going to stick with the convention I was using before. Let's call that light vector L with a yellow color, and we'll call the view vector V with that green color, just to stay consistent here. And so this is going to be our generalization of the shading model. This is our BRDF. All right. Now, of course, as I said, we're kind of taking these cosine factors out of the shading model and dealing with them as separate terms or separate components in this entire radiance calculation question, where we're calculating illumination on a certain surface point, or we can call this radiance. So let's just go ahead and write out the rest of this equation. We can say again, and we want to describe the outgoing radiance from a point, or the light reflected off a certain surface point, as so we'll call it like light outgoing from a certain surface point, right? This vector is basically defining an outgoing vector from a certain surface point. That will be equal to our BRDF times the incoming radiance from our light sources. So we're going to introduce that as a really another function here. We'll just call that so L for light again, but in this case incoming, not outgoing. This is our incoming radiance. Again, it'll be a function of this light vector, and we'll multiply that by just one more component here, which is just going to be the again, the normal vector, taking the dot product between the normal vector and, again, that light vector. All right, so, and again, we should label those. This is the incoming radiance, and this is our cosine factor. Now, we're not going to go into a crazy amount of depth with BRDFs here, but let's just understand that all this really means is that we're saying that the incoming light radiance is modified by the BRDF, right? It's modified by some behavior of the surface material itself, and finally scaled by the cosine factor. And we saw what that did before when we were talking about diffuse shading, how that changes the final lighting intensity at that surface point, depending on the position of the light source compared to, and that incoming light vector compared to the normal vector. All right, so that's really all that's happening here. And just a few more things before we move on to the next section here. So far, we have been dealing only with BRDFs. So BRDFs, which again stands for bidirectional reflectance distribution function. This it specifically deals with scenarios where light is reflected off a surface, right? As the name suggests, right? However, of course, there are material types where light actually passes through an object, right? So in order to take into account light transmission, we also have bidirectional transmittance distribution functions, right? So again, as the name suggests, these deal with material models which have light actually transmitting through the object itself. And something you're going to find in modern 3D packages is really a generalization of these two methods here. It's a generalization in that it allows us to take into account both reflection as well as possible transmission as well in a single material model. And this is called the bidirectional scattering distribution function, or BSDF. All right, so the BSDF is just a generalization of these two types of material light interactions. All right, and while BSDFs take care of most material simulation requirements, there are certain situations where we need to deal with another type of material light interaction, and that's where we have an incoming light vector, and instead of either passing right through the object or being just reflected right at the surface point, the light might enter the object and scatter around a little bit before exiting the surface at a different place. And this phenomena is called subsurface scattering, or just SSS for short. And in the context of these functions that we've been talking about, subsurface scattering is introduced into something like a BSDF as actually another type of function which deals with incoming and outgoing vectors, and it is called the bidirectional surface scattering reflectance distribution function. So a bit of a mouthful, but yeah, the BSSRDF in the context of these bidirectional functions that we've been talking about, where we're dealing with just incoming light vectors and outgoing view vectors, really, the BSSRDF is where we are able to start working with subsurface scattering. And let's just take a quick look at subsurface scattering just so we understand exactly how that works. So for the majority of applications, the BSDFs that we've looked at so far will work quite well. There are some situations, however, where we're viewing certain substances like skin or marble or milk maybe close enough that we expect to see the results of light actually entering the object's surface, bouncing around a little bit and then exiting at another location, right? So if I add some subsurface scattering to this material model here, we can start to see the effects of this, right? So again, without subsurface scattering, this is just call this like a normal diffuse surface. I could actually turn the roughness down quite a bit and we could see a nice specular highlight there. But if I start introducing subsurface scattering, what we're doing is we're enabling light to actually penetrate the surface of the object, scatter a little bit and then exit. And particularly, we're allowing light on the red side of the spectrum to scatter and exit the surface. Right, so this is subsurface scattering, and it's actually kind of interesting to note that in reality, all diffuse reflection is actually a result of subsurface scattering. However, usually the scattering is so minimal or that we view the object from such a distance that the material might as well just be shaded using a diffuse shading model or just a normal BSDF, which is definitely less computationally expensive than doing this whole subsurface scattering simulation. But in certain situations, however, actually doing this whole simulation of the light scattering around inside the object is going to be essential to achieve realistic looking results. So again, and we can just run a few different scenarios here. Maybe we can move the light source behind a thin object and maybe move it off to one side, something like that. And we can really start to see what is happening here with subsurface scattering. Of course, with the light off to one side here, showing us that there's quite a bit of light that has been permitted to enter the surface of the object and scatter and exit on this side, not so much on the other side here. Of course, again, contrasting this to completely turning off subsurface scattering where there is no illumination whatsoever, right? With the light source only on one side of the object, it is only possible to see this interesting detail with the simulation of subsurface scattering. All right, and that is the BSSRDF, the bidirectional surface scattering reflectance distribution function that allows this to happen.